Okay. So we'll start off linear algebra with Euclidean M space, which involves vectors and associated topics with vectors, basically is what this section is on. It's sort of an overview of a couple vectors, terms, a series or two, and such. Well, let's quickly go over a couple detailed things for this section, especially because vectors, it's in Calculus 3, you also see vectors. So some of this is familiar to people who take Calculus 3 before linear algebra. They have a basic idea of especially this section, some of the ideas. So we define them in this area of mass as in the Euclidean M space, which is R, like a bold R. So I try to shade it in sometimes with an M. It's like a exponent, like it's raised, M, R to the M. And M is like any integer, basically, any positive integer. It can be 1, it can be 2, etc. 3, 4. You can have any number. And basically, when you have a vector like that, you have U, and this is like if you have U is a vector, that's why I have an arrow above it. So R is, it's any vector and it has its own components, U1, U2, etc. to UM. And U1 to UM are real numbers. So vector U equals 2, 4, 7 is vector in R3 because there's 3 components. And the 0 vector in general is 0, 0 for however many dimensions there are, basically. So the 0 vector is always 0 though, every component. Every component is 0. So if you're given U equals, U is a vector and V is a vector, basically. That's why it's to M and M, like they're the same dimensions. The distance between these two vectors, U and V, is just, it's a formula from other classes, I believe, as well. Down here, the distance between the vectors is V1 minus U1 squared plus V2 minus U2 squared plus all the same thing until you get to the last component, VM minus UM squared. So it's just the addition of the squared difference between each component. And you take the square root of it in the end when you sum everything up. And the lengths of an individual vector is given with these sort of double brackets on both sides. It's just the square root of the summation of each component squared. Oh, and if you have a scalar, you multiply by any vector. You just multiply the scalar to each component. So you have CU1, CU2, etc. for C times vector U. And if you have vector V equals C times vector U, vector U, then U and V are collinear vectors. If C is positive, then they're the same direction. C negative, then the opposite direction from each other, two vectors. But they are collinear if they have this format, so this equality. So a very important theorem is we have vector U be you let U be a vector and C be a constant. Then the lengths of C times U equals absolute value of C times the lengths of U. And a unit vector is a vector of lengths equal to 1. Here's another statement we need to digest. So the lengths, basically, sometimes it's called magnitude as well as another term for this, but lengths works very well as well. Yeah, the lengths of U is equal to 1 is what a unit vector is. So you have a unit vector, its lengths will be 1. And here's another thing to note is that you add or subtract addition or subtraction between two vectors. You just add or subtract the individual components. The dot product between u and v, so u dot v it's called, these two vectors, it's just u1 v1 plus u2 times v2 plus u3 times v3, etc. to get this um times vm. You just add them all together and you get a single number. So it's no longer a vector. It's sometimes called the scalar product. You know, especially in physics, they'll sometimes call it that because you get a scalar. It's not a vector anymore. It's just a number. And if the dot product equals 0, then u and v are orthogonal vectors, which basically means the angle between the two is 90 degrees. If you're able to see, especially in 2 dimensions, you can see that. So you let P and Q be 2 points in Rm. So then you have P equals P, different points, P1, P2 to Pm, and Q equal Q1, Q2, and Qm, and these are just points. Coordinates, as you will. The point is that the line connecting P and Q, so P1, P2, etc., not points. Those are like its area in each dimension. So you have like its x coordinate, its y coordinate, etc., etc. Sort of like when you have x and y coordinates, since one point has two things, like in 2 dimensions, you'll have x equals 1, y equals 2, and there's a point there. That's what P is here, and Q, same thing for however many dimensions. And that's something you have to consider, is that you can't really draw these out unless they're 2-dimensional or maybe even 3-dimensional at times, but you can't really draw out 4 and above dimensions. But it's the same principle. But yeah, line PQ, no matter what it, has points x of t equal 1 minus t times p plus t times q. And t is a parameter, which is just a number, a real number. If t is between 0 and 1, like the value is anywhere between those two, it gives you, if you're only considering those points, then it gives you every point on segment PQ, a segment. So everything between P and Q. And you see if you let t equals 0, it's 1 minus 0 is just 1, so it's p plus, just p plus 0, because t times q would be 0. So you just get p, and then 1 is the same thing, you just have q. And everything in between 1 and 0 will be points on that segment. But yeah, the equation of a line, though, between 2 points is just 1 minus t times p plus t times q. And another form is point. This is 2-point form. Point parallel form of a line is just slightly different. It's x of t equals p plus t times q minus p. And you can convert between the two forms, and I'll show you that at the end of this section. I'll show you how to real quick. You can quickly, as long as you understand one of them as a specific form and the name to it, you can just switch to the other very easily, as long as you know exactly one of them. You can kind of remember one of them specifically and just have an idea of the other one, you'll be able to switch. And parametric equations of a line is something briefly you can look at as well. If you'd go from this form, p plus t times q minus p. So q minus p is just, it's an individual number itself, because these are two numbers. So you'd get p plus something times t. So you'd have 2 minus t, 1 minus 2t, etc. And you just do each of these individually. So x1 equals 2 minus t, to x5 equals 1 plus 6t. The whole idea. And one more thing, planes in Rm, you have a 2-vector plane as s of t equals s times u plus t times v with the vectors. And s and t are parameters. And you can have a plane determined by 3 points. Is a very interesting one, p, q, and r, let's say. It's x s of t, so you have 2 parameters instead of 1. Like with a line, you have the 1 only. It's p plus s times q minus p plus t times r minus p. And a line is always just p plus t times q minus p for the one form, the point parallel form. But this is the comparison. So line is like that, plane you just add on. And you subtract from the same point each time is what you're adding on. So it's p plus s times q minus p. So again, q minus p, and then plus another parameter times r, the extra point, minus p. So p, p, p. Just to keep it consistent, you can have 5 or 6. You can have a 6 space, a 7. You're going to keep it up. And there's a problem like that that involves a 3 space. So now let's look at some examples, since I've gone over a decent overview of vectors and everything. In the Euclidean M space, so we're just doing operations for a lot of these problems first. So you're given these vectors, they're in 4, they have R4, so 4 different components. And we perform the following operations on them. So addition, you have u and between u and v, it's just adding them. 2 plus -1 is just 2 minus 1. That's another thing you have to remember. Addition of a negative is just subtraction of the regular number. But that's elementary. And so it's just, you just do the addition here, and then you get 1, 2, 5, 1. This time it's just multiplication. It's multiplication and addition for number 3. So 2 times u plus 2 times is saying u plus 2v plus 3w. You just multiply it through, so it's 2u plus 4v plus 6w. So then you do the multiplication of scalar. So it goes in, so 2 times this vector, you get 4260 from 213, 0. Same with here, 4 times this, so 4 times -1 is -4. 4 times 1, 4. 4 times 2, 8. 4 times 1, 4. And same here, 6 times it. And the vectors are colored as above and put in. And when you get your things multiplied, so you just add them, and you just add each component, all the 3 components, and you add each component by component. So 4 minus 4 plus 12. 2 plus 4 minus 12, and so on. And eventually, then at the end, I reevaluate, just saying that 2 times the same from the beginning is equal to 12's -6, 14, 40. That's your final answer. Oh, the dot product, here's an example of it, v dot w. You multiply -1 times 2, because these are each the first components, and the second component of each vector, 1 times -2. Third component times third component, 2 times 0, and 1 times 6 for the fourth component. And you add up what's multiplied together. And you get 2. It's just 2. Now we're doing a lengths problem. So the lengths of 3 times w, well, you can split it, so it's the absolute value of 3 times the lengths of w, so it's just 3 times the lengths of w. And you just do your formula from before. It's a formula I listed at the beginning. And then goes through all the mass. And simplify it down, because the square root of 44 is the square root of 4 times 11. So that's just the square root. That's just 2 times square root of 11. So it's 3 times 2 times square root of 11. So it's 6 times square root of 11. No, basic operations like this are not the most complicated things. It's just you have to follow a formulaic process for some things. Other things take some interesting thought and everything. Here's the distance problem. So v and -u. So you multiply -1 into the vector u, basically, is all you're doing before you do anything else. Put that in brown. So 2, 1, 3, 0, so it's -2, -1, -3, and 0. And when you subtract the negative, you're just adding the number. So, and I even wrote this down, so it's, right here. It's thrown here just in case. Any confusion. So, and you do the distance formula, which is this formula, and then you eventually get square root of 31. You cannot simplify square root of 31 into anything. You can't, like, 31 is a prime number, so you can't really do anything. And number 11 here, we have the lengths of 2 times vector v minus vector w. So the way you approach this is you use a subtraction of vectors first, which is a very simple operation. Just -3, 3, 2, and -5. And then you do 2 times that to get -6, 6, 4, -10. Then we just do the lengths of this. Take square root of what you get inside and simplify it down. So you get 2 times square root of 47. Because 188 can be divided into 4 and 47, and square root of 4 is just 2. So you do it. So which pairs of the following vectors are orthogonal? Since that was brought up, and that's with dot products, something that can be talked about. So here we have 4 vectors, and we're checking each pair. So there's a decent amount of work here. So U1, U2, U3, U4 is color-coded. So they're only orthogonal if it's equal to 0, the dot product. So normal dot product process. Again, we end up with U1 and U3 being orthogonal, U2 and U3, U2 and U4, and U3 and U4. So the only ones that aren't are U1, U2, and U1, U4. As you can see, if it's equal to 0, the dot product, and they're orthogonal. Anything else the dot product equals, if it's not equal to 0, then they're not orthogonal. But all the math is shown here so you can see how it works. Just good practice with the dot product there, but now. So now we want to find the unit vector with the same direction as 2, 1, -1, 0, 3, 4. So we have a R6 vector. So we let v equal 2, 1, -1, 0, 3, 4 as described. And we want u such that the lengths of u is equal to 1. Now, in general, there is a formula for this, but it's good to work it out sometimes to see where it comes from in almost a proof-like fashion like this. This is a semi-proof, not a full-on proof, but it's sort of a proof in it as well. And it's showing how this formula comes out. But there is generally a formula for finding a vector with the same direction. Finding the unit vector with the same direction as this individual vector. So u is equal, so the length is equal to 1, and we also know that vector u is equal to c times v because it has the same direction, where c is greater than 0. So we have these two conditions. So we can go from there that the lengths of u is equal to lengths of c times v. So, and lengths of u is 1, so it becomes 1 equal to absolute value of c times lengths of v. And absolute value of c is just c, so it becomes 1 equals c times lengths of v. You divide both sides by lengths of v, and you get c equal to 1 divided by lengths of v. So the lengths of v can be calculated through that simple formula, and we eventually get square root of 31. So the lengths of v is equal to square root of 31, means that c equals 1 divided by square root of 31. So we go back, we have u equal to c times v, hold up. So it's just u equal to 1 divided by square root of 31 times the vector v. And I'll give you your unit vector. So you multiply the scalar in and you get it. And in general, u equals 1 divided by the lengths of v times v will give you the unit vector in the same direction as your vector. You know, it's the same direction, of course. That's why it's generally speaking. Yeah, these two conditions give you a general formula. Regardless, if you check this, if you take the lengths of of this vector u, you'll get 1. So you can check on your own if you want. Give 2-point and point parallel forms and parametric equations for the line in R4 determined by these 2 points, P and Q. So 2-point form is just x of t equal 1 minus t times P plus t times Q, so you just plug in. There's not anything else to really do. The point parallel form is x of t equal P plus t times Q minus P, so you know that. You plug it in. Oh, and here, Q minus P, so you plug in the individual components, each and subtract. And we get this. In parametric equation, use point parallel form. Yeah, you distribute the t in. So it's -1 plus 0, 0 plus 0, 3 plus t, and 2 plus 3t. So it becomes just x1 equals -1, x2 equals 0, x3 equals 3 plus t, and x4 equals 2 plus 3t. And the trick I was talking about earlier is x of t equals 1 minus t times p plus tq. You distribute the p and you get p minus pt plus qt. Well, you can mess around. You get x of t equal p plus qt by rearranging minus pt. And then you have to distribute out the t, so you get p plus t times q minus p. So that's the two forms. You switched between them in a couple elementary steps. Very simple. So you can recall one only and work out the other formula. If you don't have a perfect idea of both, but you know one of them very well, you can just, and if you know what it's called especially, then you'd be able to, even label it. Like, here's the 2-point form, and now let's get the point parallel form from it. And vice versa. No, very simple distributive property stuff. So, and 27 is explain why the equation fails to be linear. This is very basic, so I have a couple other examples I added in. So we have x1 plus 2x2 plus x3 minus x4 times x5 equals 3. Product of two variables means it's no longer linear. Fails on that alone. X squared plus y squared equals 0 would also fail to be linear due to product of two variables. So x squared is just 1, y squared as well, but x times x. So and another common one is a trig function of the variable. Also makes an equation nonlinear, so x plus 2 times sine y plus 3z equals 0. It's not nonlinear because sine of y. Any complicated function, like trig functions especially, but also like exponentials, would make it not linear, really. Logarithm, I think, is the other common one. It's no longer linear. It's logarithmic then. But yeah, that's just a good thing, and we'll go over it again in the next section. Briefly as well, linear stuff. So describe the series space determined by the points 3, 1, 0, 2, 1, 2, 1, 4, 2, 0, -1, 2, 1, 3, 1, and 0, 2, 0, 1, 0. So each of these gets labeled a letter, P, Q, M, and N. So P, Q, M, and N. That's why I labeled them. So 4 letters. And in general, you have just one less parameter when you're making a space, like a 3 space or a plane. Like a 3 space is just a type of plane, basically, like an advanced plane. So it's 3 space. There's one, 3, and there's 4. There's 4 points, so 3 space for the plane. 3 variables. And I think it would be called a 4 space with 5 points, basically the same idea. And you'd have 4 variables. 4 parameters. So it's p plus r times q minus p plus s times m minus p plus t times n minus p. So minus p minus p minus p. So p plus r, so parameter times q minus p, plus parameter s times m minus p, so minus p again, plus t times n minus p. So that's basically the format in general. You're just adding, you have this point, you have one point you take it from, because in theory you could take it from any point and it would be fine, but you have to keep that point constant. So I chose p, so you subtract p, subtract p, subtract p from each of the other points. And p is by itself at the beginning. So you do all the math, you basically just do the subtraction and then distribute in the parameter. The parametric equations become then, it's x1, so we have x of r st equal this thing with all the parameters times the points. With five things in each 5 coordinate system. Yeah, it's a 5 coordinate system basically. So parametric equations is x1 equals 3 minus r, so it's 3 minus r because negative 1 times r, minus 4s minus 3t. And same thing for each of these. And that's all. Basically, that's the best way to describe it, is to give the give this the plane equation, the 3 space, and the parametric equations is enough to describe it, generally speaking. Because you can't draw this out really. It's not going to be drawable by a person, at least. And even on it's pretty hard. You can't really imagine what it looks like. But it's an interesting concept to still do theoretically and on paper and pencil. But that's it for this section on the Euclidean M space.